Welcome back, folks. Today is day 86 in our circles unit. And you remember last class, we talked about the fact that I'm giving you an option. You can either follow the traditional course and each day come in, get a worksheet, take the notes, do the practice problems, turn it in as homework, and build your way towards understanding. Or you can step out of the normal track and do an alternative assignment instead of homework to demonstrate proficiency in one of these skills. What I'm handing you now is the skills listing for the entire unit. So if you're going to be independently learning this unit, this is the document you'll use to guide that learning. Let's start off by looking at the ones we've already covered. We've covered Circ 1. Let's take a look. Can you identify the radius, the diameter, the chord? If, as I say these terms, they don't mean anything to you, I suggest you circle them. Secant, tangent, circumference, central angle, arc, intercepted arc, minor arc, major arc, lieutenant general arc, just kidding, measure of arc, semicircle, length of arc. You should also be able to define a circle and name it correctly by the center point. Any questions right now about things that show up here that you have no idea about? Yeah, right. So when we talk about things like a central angle, picture it like a little flashlight. And when the angle shines, it shines on a portion of the arc, and this is the arc intercepted by this angle. Similarly, if we were talking about an inscribed angle, these two angles share the same intercepted arc. Good question. Other questions? Okay, but you give yourself a score of 1 through 5 next to that. 5, I am master of all these terms. They make perfect sense to me. I could easily both point them out and describe them to others using appropriate vocabulary. 3, most of these make sense. I have a general understanding of these concepts, but there's a couple I can work on. 1, I don't believe in circles. I don't think there's an ability to have perfectly round at all. Second one, Circ 2. Given a central angle, find the measure of the arc intercepted. Let's visualize that for a second. Here's a circle. What's a central angle? Nice use of vocabulary, an angle with a vertex in the center. And if I know that, for example, the arc that is intercepted by that central angle is 50 degrees, how big is the angle itself? $25? Fair guess. Wrong. Let's put it this way. Let's say that you're eating a pizza and you get a slice of pizza that has 50 degrees worth. Would you agree that as a fraction, that's 50 out of 360 of the crust? That's how much of the crust you get. And for me, at least, the best bite is that little center bite in here with all the cheese. And it's kind of a little bit rich with more stuff on it. And I would also get 50 out of 3/60ths of that, wouldn't I? So in other words, when we're talking about central angles, that central angle is equal to the same measure of the arc that it intercepts. What I think you were thinking about when you said 25 was Circ 5. To find the inscribed angle, and given an inscribed angle, find the measure of the arc intercepted. Now, I can't really fit this in here very well, so if only we had some way to like look at pictures that were better representations of this. Look at that, flip this over. These are the same images that you used to describe what you see. And now what we're going to do is we're going to put formulas in every one of these boxes. And in this unit, this will be your Bible. This document will have everything you need to know to be able to satisfy all the problems in the unit. What does this picture represent? A central angle. Well done. And we know that because it's got a radius intersecting a diameter at the center. So up here, write central angle. And if I have a central angle, where this central angle is measure A, and the arc intercepted is arc of measure B, what's the relationship between A and B? They're equal. So that's our formula. A equals B for this picture. Jensen, you looking for something?
Just one of those.
Yeah, here, come here. I got them up here. Anyone else missing this sheet? Mm-hmm. All right, let's come down here to this picture. What's this picture? The fifth one, right? What do we call that? Inscribed angle. So write that. And can somebody use appropriate vocabulary for me to describe what this picture shows? What do you call these segments that have endpoints on the circle? Chords, good. And so we have two chords with a point of intersection on the circle. This is then called an inscribed angle. And what's the relationship between an inscribed angle and the arc that it intercepts? Half, right? So A is equal to 1/2 of B. Now, let me ask something here. Let's say that I've got a nice inscribed angle here. And I tell you that this arc that it meets is 100 degrees. How big is this angle? 50, right? Everyone okay with that? Now, what if I take those same endpoints of this 100-degree arc and I carry them back here to make a different inscribed angle? How big is this angle? It's still 50, isn't it? Because both of these intercept the same arc. So these two will be the same. Does this picture look a little bit like this picture? So this is called the arc intercept corollary. And we talked a little bit about corollaries in the past. It's not quite a theorem because it doesn't get proven to the same degree, but we could prove it pretty easily. It's just an application of what we already knew, these inscribed angle theorems, that can be extrapolated to this case because it's used often enough. It's worth bringing out. What is the angle relationship between A and B in this case? They're equal. Two more of these to teach you now. Let's say that I keep doing this. You know how I had this initial inscribed angle, and then I made a second one that was a little closer to this endpoint. Say this is A and this is B. Could I do it again and come even closer to B? And would that still be 50 degrees? Still an inscribed angle, isn't it? Could I get even closer and still make another inscribed angle? How close could I get? Like if the circle were coming down here and B were blown up into this really big point, do you agree that I could certainly go all the way to this next point, whatever it is, and I could come right to that point and then to B, and that would still be an inscribed angle? Everyone okay with that? So what I want to bring up now is what happens if I take it even further? What if I go from this other point and I go to B directly? Well, I've lost my angle in general, haven't I? I don't have the two parts of the angle. But remember what a tangent is. A tangent runs along the circle and just kisses the circle at exactly one point. Turns out that if it just touches the same point that is the endpoint of a chord like this, this angle will still be inscribed. Right down here. If I have a tangent and a secant, this angle formed does intercept an arc, and it's still going to have the same relationship as if it's an inscribed angle. So I call this the extreme inscribed angle, which means what's the relationship between A and B? If the angle is A and arc is B, one half again, right? It's just like the regular inscribed angle. And if that's not totally settling in for you, try this. Let's say that I have a tangent. How many degrees are around in a circle here? 360. And because a tangent only hits at one point, can we agree that we're not losing any of the arc? It's still 360 all the way around. And if I draw myself some secant, and I don't know, let's say it's 100 degrees again, I'm contending that this is an inscribed angle, so it would be how much? 50. And if the whole circle was 360, and I've lopped off an arc of 100, what's left up here is how much? Yeah, 260. And if that's 260 as an arc intercepted by this angle, that would also be an inscribed angle. So it's going to be half as much of 260. So how big would this be? And is there anything you see that would help validate that that's true? It's supplementary. It forms a linear pair with the tangent, doesn't it? So if a tangent meets a full circle and a tangent is 180, it has to be that 1:2 ratio. All right. What about this one? Looks like there's less information given. But is it an example of the extreme inscribed angle? Jensen?
Well, each of the right angle of them.
Yeah. Because it is an example of this, right? It's got a secant meeting a tangent. This secant just happens to be what kind of special segment also? Diameter. It's cutting it exactly in half. And therefore, this arc is what kind of arc? Semicircle, good, which means it's 180. So if A is half of that 180, in this scenario, A is going to be exactly 90 degrees every single time that a tangent meets a radius or diameter. So this is called the radius tangent theorem. Lost my O. Any questions on those things we've just gone through? We're starting to fill in some of these formulas. We still have a lot to go. All right. Please move on to the other sheet, chords and arcs. I'll teach you this content, and as we fill in this content, we'll also fill in our notes. So what we're going after here is chords and arcs. And we're saying that two chords are congruent if and only if. That brings us back, doesn't it? We haven't used that in a while. What does if and only if do? What's it called? Good, a biconditional, which means it goes in both directions. The arrow goes both ways. And so if these two chords, A, B, and C, D are congruent, if that's our conditional, that's the hypothesis, then what also must be true? Let's see. I'm given that these two things are the same size. And what have we done in this class to prove most things? What geometric shape have we brought into play?
Triangle.
Triangles. So let's do that. I'm going to make a triangle to this endpoint. and a triangle to this endpoint. Can you tell me anything about this triangle? It's pretty. What is this segment? It's a radius. And what's this? Also radius. And what's true about the two radii in a circle? They're congruent, which makes this triangle what kind of triangle? Isosceles. What if I then come over here and draw the same type of thing over here? What do I know about these two legs? They're congruent. So what's true about these two triangles? Good. They're both congruent and similar, aren't they? They're congruent because all the corresponding sides are congruent. I could also say that they're similar because everything that's congruent is also similar, agreed? Now, if these two triangles are congruent, which they are, CPCTC does what? Yeah, corresponding parts of congruent triangles are the same. So if I picked other parts that correspond, like the vertex angle between the two congruent sides, those two components would also be the same size. And if I'm coming out of the center to make this angle, what kind of angle is this? In a circle, this is called what kind of angle? It's not quite vertical because these sides don't form straight lines or opposite rays. Central angle, good. And the central angle is equal to the arc that it meets. So if these two angles are the same, what's true about these arcs that they meet? They're also the same. So what we're going to say here is that if the chords are congruent, then the arcs are also congruent. If and only if the corresponding arcs are congruent. Okay. Now let's come back to this picture here for a second. And we also said that these two triangles are similar. And yes, they have a scale factor of 1. One of the rules we learned about similar triangles is that if the triangles are similar and we draw non-trivial segments, in other words, segments that are meaningful, like an altitude, what's going to be true about those altitudes? They're going to be in the same proportion as the other parts of the triangle. And so if these triangles had a ratio of 3 to 2, these altitudes would be in a ratio of 3 to 2. In this case, the triangle's ratio is 1 to 1. So what's true about these altitudes? They're congruent. In other words, two chords are congruent if and only if the chords are equidistant. From the center. Remember that we measure distance from a point to a line, not by going to the diagonal corner or the middle point. You always go perpendicular. That's the shortest distance. And if we were to measure that shortest distance in these two shapes, it would be the same. So therefore, if CD is congruent to AB, then what do I write here? Chords are equidistant. This chord is how far away from the center? EG. And I would expect that length of EG to be the same size as what other length? Yes, EF. Good. My notation right here, No. I left off the little segment tines on top, but I also left off the squiggly thing. So I'm saying the length of EG is equal in measure to the length of EF. So this is correct. All right. Let's go back to this picture again. See this little triangle here? And this triangle here? Anything true about those two? They're what? Similar? Why? They've got this side the same, and then they've got a reflexive side. And if this is a right angle, isn't this also a right angle? So are these two shapes just similar, or are they also congruent? They're congruent by RHL, right angle, hypotenuse, and leg. We then know that with CEP, CTC, if these two triangles are congruent, aren't these little sides over here also congruent? So if I drop a radius into a chord such that it's perpendicular, what's it going to do to this chord? Split it in half or bisect it. If a diameter or radius is perpendicular to a chord, then it bisects the chord, and it's what? Well, let's see. If we know that these two triangles are congruent, then CEP, CTC not only tells us these sides are congruent, but also that these little angles in here have been cut in half. So if I continued this down to make a radius hitting the side, what would be true about this arc and this arc? They have to be congruent as well because they're intercepted arcs from now congruent central angles. So it bisects both the chord and its arc. So in other words, if the diameter or radius is perpendicular chord, let's go with if EI is perpendicular to CD. Is that orange hard to read? A little bit. Then it bisects the chord. So then CG is equal to DG, and CI is equal to DI. Like my notation. Say again? For the arcs, if I'm talking about these objects being compared, I have to add the congruent sign in here to say that the arcs are congruent. Or I could choose to put a little m in front of each of them and leave them as equal and say that the measure of the arcs are congruent. So for this page, these 6 problems, what you're going to be doing is simply identifying what's given to you. In this case, we're saying, all right, so the segment SR is congruent to the segment ST. That's what's given to us. And then let's build that into an equal a if-then statement, a conditional statement. If the chords are equal, what do we know is true? We know that the arcs must also be equal. So I'm going to say that SR is congruent to ST. And since these two things are congruent, I can replace them with their components. As you suggested, 115 is equal to 7x plus 24 minus 24. 91 equals 7x. Divided by 7. 13 equals x. I'll apply the symmetric property because I like to have x first. X is 13. 5. Easy peasy lemon squeezy. I got this. 3. I sort of get the idea. That's kind of a lot of theorems. I'm going to need these notes in front of me to do this. 1. I don't understand how you did any of this stuff. Okay. Good. Any questions? All right. Numbers 5 and 6, you're going to have to think a little harder, but they're the same types of problems. So keep thinking about these rules, and you should have success with this page. Flip over to the back side, please. And let's take a look at number 3 first. Take a look at it and see how you would solve this problem. Find the value of x. Think about what we just did with the if-then statements. What conditions are present in this picture that lead us to a valid conclusion? We've been talking about chords and arcs. Do we have any chords here? We do. And what's intersecting with that chord? Yeah, part of a diameter, part of a radius, because it's coming out of the center, isn't it? And it's not just intersecting, it's perpendicular. So what do we know happens if a radius intersects a chord perpendicularly? It bisects it. So this 8-unit long chord is now broken into 2 even parts of 4 and 4. But how's that going to help us find x? Yeah, man. Like that? Super clever. Very good. So this length is called the what? The radius. How many radii are there in a circle? Infinite. And they're all the same, right? And so what Mia saw was that if we take that radius and like spin it around to make ourselves a nice triangle, we've got a right triangle. And if we have 2 side lengths in a right triangle, we can find the third. We could go the slow process. We could say 3 squared plus 4 squared equals x squared using Pythagorean theorem. But if we learned our Pythagorean triples, we remember, like John McGovern taught us, that 3, 4, what? 5. You did meet him? No. I met him. Good guy. He uses 3, 4, 5 triangles all the time on top of a roof and needs to make a right triangle. So x is 5. And again, this would work too. 9 plus 16 equals x squared. 25 equals x squared. X equals 5. Can we do something similar with number 1? You guys look at number 1, see if you can do that one, please. Any thoughts on how to solve number 1? Yeah. Okay. You got this. Use the right vocabulary. Someone help him out? A chord, yeah, good. Chord. And so if this radius is perpendicular to the chord, what happens to the chord? If a radius is perpendicular to a chord, what happens to the chord? It's cut in half or bisected. So this part's 8, this part's 8. 8, 10. How'd you know that was a 6? It's another Pythagorean triple, isn't it? Because this is 10, which is 5 times 2. This is 8, which is 4 times 2. So this side must be 3 times 2. Boy, John McGovern's coming in handy, isn't it? All right, I'll let you guys figure out 2 and 7. They will require a little bit more creativity, but think about that same idea. Break any radii into something at a different angle that gives you right triangles. Okay, last piece for today. If I give you a circle, and let's say that I tell you that the radius is 6 inches long, and then I give you that the central angle is 90 degrees. Let's call this A and this B. And I want to find the length of arc AB. Like, let's say that, well, I did 6 inches. It could be 6 meters also, but let's say that I had a really small dog. Say that I've got a pet ant, and I want my pet ant to be on a leash. And I want to find out how much I need to pave so the ant has a nice clean run around here. How much is this? How long is this? 90. It's 90 degrees, but that's not the length of AB. That's the measure of AB. And it's important, but it's not the done part of this. How long is the path all the way around in the full circle? What do we call that? No, 360, that's the measure. There's circumference. The circumference is a formula, 2 pi r. It takes into account how wide the radius is because a bigger circle has a bigger length around. So in this case, the circumference would be 2 times pi times 6 or 12 pi. If we want to know the length of this piece of it, why divide by 4? You're right. Yes, because 90 out of the total possible 360 ends up being a quarter, doesn't it? So if we multiply that by the whole circumference, then what we'll get is 1/4 of 12 pi, or that length is 3 pi. And sure, we could get a decimal approximation of that if we wanted to. It's really small, sorry. So let's generalize that. Over here, let's give ourselves a circle. And let's say that we've got some radius r and some arc measure of x degrees. And again, let's go with AB. Then the length of AB arc is equal to what? Well, the whole circumference is how much? Two pi r. But we don't want the whole circumference. How much of it do we want? The degree out of 360 work. That fractional part of it. So we're running a little tight on time. I'm going to make this a little faster for you here than you figuring it out. Do you agree that this 68-degree angle and this angle next to it, CED, are a linear pair? So I could find this angle by saying 180 minus 68 is 112. And this is a central angle, so that means this arc is 112 degrees. Does that answer the question of the length of CD? Nope. The length of CD would equal that 112 out of 360 times 2 pi r. And we're told that our radius is 15. Once you get it to this, you can just plug it into a calculator. So I'd say 112 divided by 360 times 2 times, use the pi button, please, times 15. 29.3215, it says round to the nearest 100th. So let's give it squigglies, 29.32. And because these were in centimeters, this will be in centimeters. Okay, please wrap this up. This is your homework 86 to complete these sheets. Just this sheet. The formulas will fill in later. Thank you very much. I appreciate it.